Hi guys, my name is Hao Tu. I'm a PhD candidate from my chemical engineering department. And in this presentation, I will talk about how to harness machine learning to advance battery management for air taxis. So I want to start by providing an overview of urban mobility today. So imagine you live in New York City, and then you want to drive in the morning rush hour to Manhattan. What will you encounter? Traffic congestion, right? So in fact, traffic congestion in the US in the only last year, we lost $70 billion due to traffic congestions and in the form of loss of time, working time, and also wasted fuel. And on average, each driver in the US spent 43 hours in the congestions. And we have 2.38 million people got injured in a car crash. So let's imagine another scenario. Now we live in Kansas, right? And this figure shows the population density in the Kansas. And if you have a company based in Wichita and you want to do business in Lawrence, and if you want to drive from Wichita to Lawrence, it takes you 2.5 hours drive. And if you need to commute between these two places frequently, then it will be very time consuming. And what's more is that if you have extreme weather conditions such as snow, right, and then the road will be closed, so the time will become infinity. So the question now comes to what will be the future of urban transportation? So the future of urban transportation will make us to unlock the aerospace. And this is, we need to leverage the electric vertical take-off landing aircraft and also called air taxis. So these air taxis are vertical take-off landing, so do not need a runway, and the size is similar to your car. And then this electric aircraft also is fully electric, so does not have any carbon emission. So it can help us to alleviate traffic congestion in big cities and also enable rapid transportations from rural area to city centers, and also help us to reduce carbon emissions because it's fully electric. So my research is on the battery management system. I'm a battery operations engineer, and one key functionality of this battery management system is to predict how much energy remains during the battery operation. And this quantity fundamentally have a very it's a direct indicator of the aircraft's remaining flying range during the aircraft's operation. And similarly, we have electric vehicles nowadays, right? And for electric vehicles, we also need to estimate the battery's remaining discharging energy during the vehicle operation in order to predict the remaining driving range. So now the question comes to whether this electric aircraft will cause new challenges for battery management system. And to answer these questions, this table shows a comparison between the electric aircraft's battery and the electric vehicle's battery, where the red one shows the electric aircraft's battery operation, and the blue one shows the electric vehicle's operation. And a key difference is that the air taxis require the batteries to operate at a much higher current. The reason it mainly is because we need to limit the total weight of the aircraft in order for it to fly on the sky. That means that we need to use a limited number of battery cells to give very high power throughput. So then the next question comes to whether the high operating current will have influence in the battery's remaining discharge energy prediction, right? So to answer this question, let's consider a simple experiment. So we consider a battery cell, and then the first step is that we put the battery in the room temperature, and then we fully charge the battery, and then fully discharge the battery using a constant current, using different constant current until the battery is empty. And then we calculate how much energy we can withdraw from the battery. And the result is here. What's important thing is that we can see that depending on your discharging current, the energy you can withdraw from the battery is much different. And here, we use a cutoff voltage as 2.7 volt, which is commonly used to decide in nowadays applications to decide when the battery is empty. But for this discharging current, if it is higher, then we need to add another cutoff limit, which is the cutoff temperature, because at a very high discharging current, the battery's temperature will surge tremendously. So if you consider this graph, right, the operating range of the electric vehicles is among here. So you can see the discharging current is pretty rapidly low, below 1 C rate current. And then in this way, you can find out there's the upper bound and lower bound of the available energy is not much too difference. However, for the electric aircrafts, In extreme case, the operating current can be up to 12 series. And in this way, we have a large difference between batteries' alloy energy for the upper bound and lower bound. So this points out to a very important factor that the battery's remaining discharge energy estimation for air taxis is changed with the discharging current. So we must take into the effect of discharging current into account when we estimate the battery's remaining discharging energy. So this motivates us to promote a new definition for batteries remaining discharge energy estimation, where this definition, the left-hand side is the battery remaining discharge energy, and on the right-hand side is the integration from the batteries for the future current times the voltage. And the time is from the present moment until the end of discharge criterion, which is the time when either the cutoff voltage limit or your maximum temperature limit is reached. And what's different from the existing literature is that we specifically take into account the change of future discharge current into the battery's remaining discharge estimation. So let's consider some figure explanation of this concept. So imagine your aircraft is operated at time t now, and then imagine we can predict that what if the aircraft operate at a low current, how much energy you can withdraw from the battery itself, which is the shaded area, where the shaded area is the geometric interpretation of this integration. And what we also want to can predict is that if the current I is higher in medium current, how much energy you can withdraw from this shaded area, and also for high current. And this concept shows that we can estimate the battery's energy by taking into account different discharging current for the battery cell. So now we propose a concept that it makes sense for electric aircraft. And in order to formulate a prediction problem, if you look at this integration, we need to predict the battery's future voltage and time and temperature in the future from time t, present moment, until the end of discharge time, right? So that means that we must need a battery model. So the complete prediction problem formulation is to predict this remaining discharge energy we just proposed, subject to the battery dynamic model. And we summarize the challenge of solving this problem. The first one, as we mentioned, emphasized a lot in the previous slides, is that this quantity is current dependence. It depending on the future discharging current. And also the upper limit of the end of discharging time is no longer a quantity determined by the minimum voltage, but also a quantity determined by the maximum temperature. And also the battery itself have a nonlinear dynamics. So in order to make a good prediction, the first step is that we need to build an accurate and computationally efficient battery model. And then based on this computationally efficient battery model, we need to figure out a way to accurately and computationally efficiently to solve this integration. Thus, finally, we can get the remaining discharge energy of the battery cell. So let's focus on the first question, how to build an accurate and computationally efficient battery model. Well, here we can see that the battery, although it's a small scale, but actually there are a lot of complicated electrochemical reactions inside the cell. So the lithium-ion concentrations are governed by partial differential equations. And also the ore potentials and the conservation of charge equations are governed by ordinary differential equations. And also some nonlinear algebra constraints, such as Barth-Warman kinetic. And finally, after you solve all these equations, you can get the prediction of battery's voltage. So, and what's important is that for each equation, whether it's PDEs, ODEs, or the nonlinear algebra constraints, they are coupled against each other. So you need to solve them simultaneously to get the battery's voltage prediction. So this model is very accurate, and accurate from low to high discharging current, and can satisfy our need for the electric aircrafts. But it's also computationally expensive. Therefore, researchers have developed some reduced order model from, for example, equivalent circuit model and the single particle model from a physics perspective. But these models are only accurate from low to medium current. So that's not generalizable to the high discharging current scenarios. And the ideal region is that we need an accurate model and also a computationally fast model. So the question now comes to how to reach such region, how to get a model from here, right? And then we take the approach of hybrid physics machine learning. So we consider a battery cell, right? We can firstly identify a reduced order physics-based model. And then this reduced order physics model is not accurate for high current. And then we try to use a machine learning neural network to learn the residual between this reduced order model and the true battery's voltage. And what we find out interesting is that we must fed the state information of the reduced order model into the neural network in order for the neural network model to get an accurate and physically meaningful prediction. And we can, in our paper, we explain this from the perspective of model order reduction. Somehow the neural network try to try to fulfill the gap between a low dimensional reduced order model and a true high dimensional true system. And we call this hybrid physics machine learning model. And then we specifically in the next experimental results, we use one equivalent circuit model, which was the one we developed several years ago. Let's take a look at the results. So we consider a battery tester in our lab, and we collect training and testing data under different discharging scenarios. And here is one of the testing scenarios we can see. We can see that the current operates from low to high current, which is shown in the first row. And the second row shows the battery's voltage. And what's important is that for the high operating current portion, our model can predict the battery's voltage in a very accurate manner. And somehow, we also applied a similar methodology to also predict the battery's temperature. And here is the prediction result for the battery's temperature. It can trap the truth pretty well for these hybrid modeling methods. So let's come back to this slide. We need to answer the second question, because in the problem formulation, we already define a concept that makes sense for the electric aircraft. And also we have a dynamic model that also makes sense for making prediction from low to high current. And the next question comes to how to compute this integration, which is the remaining discharge energy of the battery in a real-time manner, right? So naively, because we need to predict the battery's future behavior, so we can consider a simple methodology. For example, consider model formula simulation, right? Consider that the battery now is at present state is xt, right? And then you can forward simulate your battery dynamic model to predict the remaining energy from t to some future time t1. And you can keep doing model forward simulation until the end of discharging time is reached. And this random discharge time will be from the present moment integration of the current times voltage from the present time t until the end of discharge time correctly. So this one is feasible, but computational inefficient because the prediction horizon from t to tm can be hours depending on your future discharging current, whether it's large or small. So whether we can build a direct mapping from the present state to the remaining discharge energy quantities, to our target quantity directly, right? So this is the key. So whether we can build such a mapping. So we try to build such a mapping. We try to find out what's inside this white box. And after some analysis from physics and mathematics perspective, we found out, yes, we can use a three-step prediction approach. After we use two neural networks to learn the mapping and also the bisection search to correct the prediction, we can finally build a mapping from the present state to the end of to the battery's remaining discharging energy. And in this way, we don't need to do model forward simulation. And the key is that we must need to predict the remaining discharging time, which is the Tm here, right? But the story behind is much more complete. Rather than we need to fit the present state information of the battery into the prediction framework, we also need other quantities such as the future ambient temperature and also the future discharging current. But each steps are mathematically and physically justified in our journal paper. And we also have some theorem to prove the existence of the step 1 for the neural network, and also for step 3, this neural network. So let's consider some experimental validation. We consider 70-kilometer trip profile for the electric aircraft, which includes the takeoff, cruise, and landing phases. And then this is the operating current profile of the battery during this 70-kilometer profile. And we can see that during the battery's real-time operation, we can predict the battery's remaining energy for this aircraft in a timely manner, in a real-time manner. And what's important compared to literature is that we have additional access, which is the future discharging current. That is the one we take into account. So traditionally, it's a 2D plot if you look at the electric vehicles, but now it's a 3D plot because we have an additional access. For example, if you consider the prediction at time 234 seconds, and this point tells you at this operating time how much energy can withdraw from the battery if in the future it's discharged under a 5C current. And this point tell you how much energy for a 9C future discharge current. And this and then we selected 4 points on different operating time and different discharging current to validate the accuracy and accuracy of the prediction. And we can find out that under these 4 scenarios, the predictions, which is the green one, matches the truth blue pretty well. for all of the scenarios. And what's also important is that our methods is very computationally fast because if you apply the forward simulation methods, the update frequency of your remaining discharging energy is only 0.02 hertz. But our machine learning model can update remaining discharging energy for the aircraft at 2.5 hertz, which increase the safety for the aircraft. So conclusion, we consider a less battery remaining energy prediction problem. And this problem, the key is that this quantity varies from low to high current. And then why we use a machine learning model? First is that the hybrid physics machine learning model is better than physics-based model in terms of both accuracy and computational efficiency. And secondly, by proposing a neural network structure, we can enable real-time prediction of the remaining discharging energy for the battery cell. And the application of our study is the air taxis. And here is our publications. We have two conference papers and two journal papers published under this topic. And thank you so much.
Can you explain a little bit about the algorithm for bisexual search you mentioned? That's
yes.
The search layer.
Sure.
So that's like a key of the machine learning.
Yes.
Yeah.
Yes, you're right. Let me go back to this.
Sorry.
You're
so
right.
The first function layer gives 5 outputs. But never mind.
So the key here is to calculate the remaining discharging time in order to predict this this target quantity. But this time, if you still remember, we have two cutoff limits. One is the minimum voltage, another one is the cutoff is the temperature. And for the minimum voltage, if you consider the battery's behavior, it's relatively regular. So in that way, we can use math to prove that there exists a mapping from the state and also future current, which is this Z here, and also ambient temperature to this remaining discharging time, which only consider the cutoff voltage. But for the temperature behavior of the battery, especially at high operating current, it's pretty complicated. So we cannot use a neural network. We cannot prove that there's a neural network to directly learn such a mapping. So we try to use a bisection search to correct our prediction of the remaining discharging time. And then this TM will take into account both the cutoff voltage and the temperature limit. And after that, the integration will be in a complete form. You can use a neural network to compute this integration.
Some sort of optimization algorithm?
Yes, you try to find out when the time. So this is the first prediction from present moment until the first predicted remaining discharging time. And then we try to find out between the present moment and this time, whether the upper limit of the battery's temperature is violated. If it's violated, then we use a bisection search to find out, to correct the TM. And after that, we predict the remaining discharging energy.
Intuitively, using optimization algorithm kind of makes everything slower.
Exactly. But still faster than forward simulation. Because bisection search, you do not check every point along the future prediction horizon each time. Right? Bisection search is a very efficient search method.
Okay. Yeah.
Right. But for forward model simulation, you to check each point. But yeah, you are right. Ideally, if this one also neural network, then we can directly use one neural network to learn XT to this, but we cannot. We cannot find out such a physically mathematically meaningful mapping.
In one of your first slides for motivation,
yes,
you mentioned traveling from Wichita to Kansas City.
Yes.
Florence.
Yes.
And
right.
The roads are closed due to snow.
Yes.
Would you have flown an air taxi from Wichita to Kansas City? In our recent snowstorm.
That's a very good question. So, and similar to Tesla nowadays, as far as I know, if you drive a Tesla, which is electric pack in Alaska, the performance won't be very good because the battery have a very low performance and low temperature. But what they did is that the users can schedule using time beforehand, and then
you're going into too much detail. The answer is no.
Yes.
You would not fly an air taxi from Wichita to Lawrence in the snowstorm we had a week and a half ago.
We can. The answer is
because
yes.
That would be stupid.
Why?
Okay, second question. How is an air taxi different from a Tesla?
From the battery.
I mean, a Tesla, you've got to drive, you're pulling current from the
Yes.
battery, you've got to
Yes.
manage battery.
Yes,
Why is an air taxi different?
you do not have a road condition to restrict the movement. You can fly from point to point in a very fast manner.
In terms of battery management, how are they different?
For the high operating power. For electric aircraft, we need to have a much higher operating power during the takeoff and landing phases specifically. Because we need to limit the total weight of the aircraft. Otherwise, the batteries are heavy.
Teslas are weight limited.
No. But Tesla does not fly into the air. Tesla only on the ground. On the ground is okay. But if you need to fly into the air, you need to limit the total weight. That's why a lot of researchers in chemistry, they are searching for high energy density cells in order to make the flying aircraft more feasible.
So I guess my question is, are they counting other variables? Like, let's say you're using the flying taxi. So suddenly we're gonna get a huge, strong gust of wind.
Yes,
Cause if the taxi is going against the current,
right,
it's gonna be using more battery, right?
exactly. That's why I said under extreme cases, the discharging current can be up to 12 series. So normal operation, my bad. Look at these slides. So normal operation, we only need from 0.2 to 5 series, which is here. But under extreme cases, it could be up to 12 series if you look at the literature. And another thing is under emergency cases, when you have for example, you have 4 rotors, and if 3 of the rotors are broken, you still need to fulfill landing on the ground safely, right? That's the extreme cases. And similar for you, the wind gas, but the wind gas compared to the case I described is not severe than that, I think.
Oh, I'd say it's within that margin.
Yes.
I know the application area is for the air taxis.
Yes.
I'm wondering the process for you to develop the model of machine learning
Mhm.
can also be applied to a similar area such as drones.
Uh,
Will you also suggest that like this one model development process can also be used in the similar areas?
The answer is yes, you can, but for drones, the operating current is not as much larger as eVTOLs. So drones has been used a lot of nowadays, right? For how many years robotics people have working on drones? There's not much severe battery issues. But for this one, it's a new application. And there's a company called Joby, which they already do some experiments, real experiment in New York City for these air taxis to alleviate the traffic congestions.
Because of
But-
the weight.
Yeah, and we also talk with them. They are also very interested in our work. They ask us how to solve this high energy change with respect to the series.
I guess I have a quick question. I mean, is it I mean, right now you're doing machine learning to do some prediction, but
Mhm.
ultimately, are you optimizing anything, or what is the objective function here, just to make it kind of, to reduce energy consumption? I mean, at a high level, is there any?
Let me see. So what the mapping will build is this one from the state to this, and you can get the true prediction by simulating your battery model, and then minimize the error between your true RD and this state. No, minimize, my bad. You minimize the error between your true RD and your predicted RD to train the neural network. That's our
But
All
that
right.
one, I mean, can be used to somehow optimize the performance of your data.
can I say it again?
Meaning that, okay, so you use that one to minimize the error, right? But what would be the implication of that for the impacts?
This one is the remaining discharging time. And this, after you get this, so it's like this. If you go back to the, let me go back to the integration, the problem formulation. That's our terminal goal to calculate this. And if you can, we use 2 steps to predict the end of discharging time, which is the upper bound. And after that, the integration will be a fixed number subject to the model. That means for the third step, you can use a new network to learn the value of the integration. But previously in the existing, also in today's electric vehicles, what people did is that they forward simulate the battery dynamics from T to Tn. But we don't want to do that. We try to find out some computational efficient way to solve this problem.